So next here we're going to talk about vapor pressure. And so, like I said in the kind of end of the last video or near the end, that liquid gas transition is always happening. So it's always occurring at any temperature. If you have a liquid, some of those molecules are going into the gas phase and some of them are returning back to liquid. So vapor pressure is the partial pressure or the pressure of that gas coming off of the liquid. So it's creating a pressure in the gas phase. And so we call that the vapor pressure. Literally the pressure created by the vapor. Like, again, creative with the naming, I know. And so we can have molecules spontaneously jumping into the gas phase and spontaneously jumping back into liquid phase. One of the examples I always use for condensation, which is when you go gas to liquid, is when you go camping, you wake up in the morning and your tent is lined with a bunch of drops of water because the dew point has changed. The saturation point of the air has dropped. And so most of that water is from your breath. And so it left in the vapor phase and it jumped back into liquid phase and it will evaporate again. And so it did, exchanges back and forth. Or if you have like a soda bottle that you leave out in the sun and it's capped but it's empty, or any sort of plastic container or glass, you can see condensation will form and evaporate and back and forth. And so temperature has a huge effect on this, but it's something that we can move back and forth on. But there's always a pressure associated with the molecules in the gas phase. And it doesn't have to be water, it can be any liquid, alcohol, acetone, all the stuff I named before, octane, so on and so forth. But this is a temperature dependent process, and so as you heat something up, its vapor pressure increases. And so what the boiling point is actually where our vapor pressure equals the atmospheric pressure around it. So it just freely moves in the atmosphere. So there's a lot of details about that boiling point, and that's kind of the last one we're going to talk about here. But we can keep increasing temperature and we are going to increase the vapor pressure. That will be true for a liquid. Now we're only talking about pure substances, so these are only pure liquids. This isn't a mixture. This isn't like half ethanol, half water. This is all ethanol, all water. We don't mix them. That's not till the next chapter. It gets a little more complicated there. You can take a look at this equation and go, how could it get more complicated than that? Well, you'll find out in the next chapter. But since we're only dealing with pure liquids, we can use what's called the Clausius-Clapeyron equation, which is what I have written down here. And we can figure out what the change in that vapor pressure is as we change temperature. So here it is laid out. So it's the natural log of P1 over P2, and that's going to equal the delta H of vaporization divided by, I told you in 221, you never know where R is going to show up. This is the ideal gas law constant. So delta H vaporization divided by the ideal gas law constant R. Now we want to use the flavor that's joules per mole Kelvin. So it's 8.314 joules per mole Kelvin. Don't use like the 0.008, liters atmospheres mole Kelvin. Units are going to be all over the place. You want joules over moles Kelvin. And then we multiply that by 1 over T2 minus 1 over T1. So here's how this typically works. We essentially have 4 variables: 2 temperatures, 2 pressures. Delta H vaporization, that's a constant. That is, it just depends. Are we talking about water? Are we talking about, whatever it might be? You look it up in a table, or SmartWorks or whatever will give you that number. And so this is a constant. It just depends on the substance. This is a constant that depends on apparently the universe you're in. And in this universe, it is 8.314 joules per mole Kelvin. So constant. So that means we have 4 variables. We have a pressure and temperature that are paired. So we have a vapor pressure at one temperature, and we have a vapor pressure at a second temperature. And the way you handle these types of problems is you can't solve it unless 3 out of 4 are given to you. And so it's just a matter of plugging in and finding the unknown one. And there's some graphical tricks, things like that, that you can do as well. We'll leave that for, I'll do a practice problem with this, but in general, it's just knowing how to unwrap this and find like P1 or P2 or T2 or T1. That's what it's going to come down to. So ID your variables. Do I know P1? Do I know P2? Do I know T1? Do I know T2? Which one do I not know? Did Joe tell me all 4? Well, that's an easy problem then, right? So it'd be something like, what's the vapor pressure at 200 Celsius if it's 57 torr at, I don't know, 100 Celsius, something like that. And you got to watch out because you want all your temperatures in Kelvin. So that's the dirtiest trick that can be pulled, is we don't give you the temperatures in Kelvin. So remember, you add that 273.15 to convert to Kelvin. All right. So, and if you get an answer and you're like, well, I increased my temperature, but my vapor pressure didn't go up, don't trust that answer, because that is a trend that will hold. It doesn't go the other way. All right. And then in general, you know, this is the intermolecular forces chapter. In general, as intermolecular forces are increasing, as we get stronger and stronger intermolecular forces as we compare across different compounds, right? Because, you know, water has the intermolecular forces it has, but if we compare it to like dichloromethane or something, we get a different amount of intermolecular forces. But if we increase those, that's actually going to lower our vapor pressure. It's going to be harder for that substance to pop off into the gas phase. It has to leave all its friends behind. So here's our other trend. We don't want to forget this one. So don't get razzle-dazzled by the math too much. You know, remember these general trends, and they will anchor this process. So if you have something with more intermolecular forces, it's going to stay a liquid with more strength. It's going to be harder for a molecule to reach what you could think of like an escape velocity. If it has enough energy, if it's hot enough, it will break free of all the molecules trying to hold it back, and it will pop into the gas phase. But it also will more easily re-enter the liquid phase if it collides with the surface. So it's more likely to be a liquid. All right, so we'll do more stuff with vapor pressure, but it will be mixture. So now it'll be something that's like half and half, but that won't be until the next chapter. So we got one more topic in this one. We'll talk about phase diagrams, and then we are on to chapter 11.